Let's go to n-dimensional space. Most of the time we'll be working in three-dimensional space. So for example, in R3, every vector looks like this. So A has three components because I'm in three-dimensional space. A1, A2, and then A3. Then first thing we want to define is we want to define the scalar multiplication. Scalar multiplication. That's the first thing we want to define in our n-dimensional space. So if we take any vector a1 through an, and if we take any scalar alpha, then alpha times this vector will simply multiply every component of this vector by alpha. So the first component is going to be a times alpha times a1, and so on and so forth, up to alpha times an. This is scalar multiplication. The other operation is vector addition. So vector addition is when we have two vectors and we want to add them. So the other operation is vector addition. So let's say we have two vectors. One is A and the other one is B. How do we add two vectors? By definition, we add them component-wise. So I'll take the first component of the first vector and the first component of the second vector, and I'm going to add them together. This is the first component of this new vector, a plus b, and so on and so forth. The nth component of the first vector, I'm going to add to the nth one of the second vector. That will give me the last component of this new vector, which is the sum of those two. So this is scalar multiplication, this is vector addition, and also we have multiplication of vectors, which we call the dot product, but this is really multiplication of vectors, and we multiply two vectors component-wise. Also, we have the function absolute value in Rn, the absolute value function in Rn, which is the generalization of the absolute value function that we know. And so this is my vector A, A1 through AN. Let me call this vector A. If I call this vector A, then the absolute value of A, well, absolute value, or sometimes we say the length of A, is just Pythagoras theorem. So A1 squared plus dot 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 plus AN squared. And what that means is this, the interpretation of this number, that this is the length of this vector A. This is the length of this vector A. Length of this vector A. And we have this, well, we have this triangle inequality, which says that the A plus B, the length of A plus B is less than or equal to the length of A plus the length of B. And think of this as a triangle inequality, because if you have a triangle, so maybe this is one vector, this is A, and that would be B. So this is A plus B. So the length of A plus B, which is this, is going to be less than or equal to the length of this vector plus the length of the other vector. So the three-dimensional space, so the space looks like this. This is the z-axis, this is the x-axis, and this is y, and this is z. Okay, so in this is the vector space. So we have addition of vectors, we have scalar multiplication, alpha times a vector, and we have also multiplication of two vectors, and we have also the concept of the length of the vector in this three-dimensional space. Now, the other way how to think of the inner product or the dot product of two vectors is this way. So the dot product of A times B can be also defined, and that's exactly the same as we defined in the previous slide. That's exactly the same as the absolute value of A, the generalized absolute value of A, times the generalized absolute value of B, and then times cosine theta, where theta is the angle between those two vectors. So even if it's easy to think of this if you stay in the two-dimensional on the plane. If you have two vectors on the plane, then there's this angle between those two vectors. And if I want to compute the inner product of those two vectors, or the dot product, then I'm going to take the length of this one times the length of this one times the cosine of this alpha angle between those two vectors. Now, when you compute the dot product of those two vectors, this is a number. This is a number. This is a number, so it's either positive, negative, or zero. What does the dot product tell you about the position of those two vectors? See, this is absolute value of A. So this number is positive, this number is positive, and you have cosine theta, and theta is between 0 and pi. So let me remind for us how the function cosine looks like. So this is the y-axis, this is the x-axis. So if this is 1, then cosine, then pi is about 3 point, a little bit more than 3. So pi would be 1, 2, 3, about this would be pi. So here would be pi over 2. Pi over 2, and the function cosine of 0 is equal to 1, so the function will look like this, and then will look like that. Notice one thing, if you have two vectors and the angle between those two vectors is small, for example, if this is my vector A, and this is my vector B, and this is the angle theta between those two vectors, then when you compute the inner product of those two vectors, A times B, this is going to be absolute value of A times absolute value of B, and then times cosine theta. Notice that this number has to be positive, because theta, this angle is small, looks like pi over 4, pi over 5, so it's about, this is the angle theta. So cosine of theta would be a little bit less than 1 actually, but it would be a positive number. So the whole number would be positive. So when you compute the inner product of those two vectors and the number is positive, bigger than 0, this means that the angle is between 0 and pi over 2. What happens if you take the angle to be equal pi over 2? So take the situation, this is the vector A, this is the vector B, and let's say this is A, this is B. What would be the inner product of those two vectors? We can say right away that the inner product is going to be 0, because, well, what is this? This is A times B. The inner product is equal to absolute value of A times the absolute value of B, and then times cosine theta. But theta is pi over 2. This angle theta is pi over 2, but cosine of pi over 2 is 0. So this is going to be 0. And therefore, the inner product or the dot product of those two vectors, A times B, is equal to 0. And in fact, this is a way how to say that two vectors in n-dimensional space or in 2-dimensional space or in 3-dimensional space are orthogonal. They are orthogonal if and only if those are orthogonal vectors. And they're orthogonal if and only if the inner product of those two vectors is 0. So the inner product function will tell me something about the angle between those two vectors. When the inner product is 0, those two vectors are orthogonal, or sometimes say perpendicular. The same thing. When the angle is big, something like this, bigger than pi over 2, then the inner product has to be negative. Because see, so take this situation, this is the vector A, and this is the vector B, and let's say that the angle is a little bit big, it's bigger than pi over 2. So here's pi over 2, and maybe this is the angle theta. And notice one thing, cosine of such a number theta would be negative. So the inner product A times B, we can't be very specific just looking at this picture, but we can say that this is going to be definitely negative. Okay, so let me just say a few words now about, so now we are, let's say we are in n-dimensional space, but in fact, let's think of this just to have something to support our intuition on. Let's say we're in 3-dimensional space, and we want to define the concept of the normal vector to a given plane in that space. So let's say that this is, the whole situation is in 3-dimensional space. So this is the coordinate system, this is the x-axis, this is the y-axis, and this is the z-axis, and then we have some plane. We have some plane in this 3-dimensional space. So this is my plane. Well, let's pick any point on that plane, for example, this one. What does it mean that we have a vector that is orthogonal or normal to this plane? This means that this vector is orthogonal to every vector in that plane. So this vector n1 would be a normal vector to this plane to this plane P. And this is so because if you take any vector that is in that plane, for example, this vector, then notice one thing, this vector would be orthogonal to the given vector n. If you take another vector, maybe, for example, something like this, then this vector also would be orthogonal to this given vector. If you take another vector, something like this, for example, let's call this vector A, then this vector A would be orthogonal to this vector n1. So what does this mean? It means that the inner product of A times n1 is equal to 0. That's what it means, that two vectors are orthogonal if the inner product of those two vectors are 0. So of course, that if we have n1 and this is a normal vector, then negative n1 also is a normal vector, but will be pointing in different direction. So for example, this is n2, and this is also a normal vector to that plane. So now we can use this concept of a normal vector to a plane to describe a plane in a three-dimensional space. So here's another example. In general, we'll discuss later normal vector to a surface, not necessarily a plane. Like this is a plane, this is a plane, but we can have a surface like this one, and then we define later on, we define the concept of a normal vector. So what we are going to do is we are going to take the tangent plane to that surface at a given point, and then we'll take a normal vector to this plane. Okay, so let's see. Let's say now that we have the following situation. So we want to describe the equation of this plane. So what's given is we have given this vector n, and let's say that this vector has three coordinates, a, b, and c. So three components, a, b, and c. Okay, this vector n has three components, a, b, and c, and this is the vector n. 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 Remember that this is just every vector in a three-dimensional space has one representative. So we can bring this vector actually to this position, and that would be exactly the same vector n. This is exactly the same vector n. So that would be actually the representative of this vector. But in any case, we have this vector n. So this is given vector, given vector. And also, let's say that we have a given, let's say, point P0 on that plane. Okay, so let's say we have a given point. Maybe I'll take this point. Maybe I'll take this point. This is a point, and it's a given point, and it's a point on that plane. So now we want to describe the equation of this plane. So this is the plane of interest. Okay, this is a plane of interest, and we want to describe equation or derive equation of this plane. So this is going to be plane that goes through a given point x0, y0, z0. So this point P0 is also given. And we can think of this point as a vector. So this is a vector from here to here. So this is the vector. This is the vector P0. Let's say this vector P0 has coordinates or components x0, y0, and then z0. Okay, so what's given is a vector n, and a point. And now I want to find the equation of a plane that goes through this point and also has normal vector n, this given normal vector n. So in other words, okay, let's take completely any point on that plane, completely any point. Maybe I'll say maybe this one. Okay, so for example, maybe this point. If this is a point on the plane, I can consider the following vector. I can look at the vector from the origin up to this point. And that's a vector and call this vector P, for example. So this vector P is a completely any vector, and so let's call this vector X, Y, Z. Y, Z, and we want this point to be on that plane. So let's see. When I consider this vector now from this point to this one, from this point to this one, okay, so let me call this vector maybe Q. Let me call this vector Q. Then we have that P0 plus Q. Then we have that P0. Remember, this is this vector Q, but really this vector has a representative, and a representative of this vector Q would look like something like this, you know? That would be really the vector Q. So we know that P0 plus Q is equal to P0 plus Q is equal to P. So let's compute this Q vector out of this equation. So Q is going to be simply P minus what vector?
P0.
Xm, P minus P0. P0. Okay, so Q is going to be P minus P0. But now, what do we know of this vector Q? So Q really is this vector. This is one representative of this vector, but I can move this vector, and I can put this vector to this position. I can put this vector to this position. This is the same vector Q. So what do we know of this vector Q? This vector Q, and this vector N, this is this vector N, and this is this vector Q. This is this vector N, and this is the vector Q. So this vector N has to be orthogonal. This vector N has to be orthogonal to this vector Q. Okay, to this vector Q. Now, what does this mean that two vectors are orthogonal? It means that the dot product of those two vectors is equal to what value? What do we mean by two vectors are orthogonal?
The dot product equals 0.
Excellent. That's what it means exactly. The dot product is equal to 0. So now all we want to do is let's see what this equation says. N times the dot product Q is equal to 0. What is N? This is N. ABC. So A, comma B, comma C, the dot product, or sometimes it's called the inner product, but that's exactly the same. So when I say sometimes the inner product or dot product, excuse me, I'm used to calling this the inner product. Now the textbook calls this the dot product, and then sometimes, but this is the dot product of Q. Okay, what is Q? Q is equal to P minus P0. Okay, so what is P? P is equal to XYZ, XYZ, and minus what is P0? X0, Y0, Z0, minus X0, Y0, and Z0. Okay, so this is equal to X minus X0. This is the first component of this vector P minus Q. And then we have Y minus Y0, Y minus Y0. And lastly, we have Z minus Z0, Z minus Z0. Okay, so this vector Q is exactly X minus X0, Y minus Y0, and Z minus Z0. Z minus Z0. and that's equal to 0. Okay, now let's use definition of inner product. What do we mean by multiplying one vector by the other one? We do so component-wise. So I have A times x minus x0, A times x minus x0, and then plus B times y minus y0, B times y minus y0, and lastly C times z minus z0, C times z minus z0, and that's equal to 0. Okay, so that's exactly the equation of the plane that goes through this given point x0, comma y0, comma z0. This plane will pass through this given point, and not only that, the normal vector to this plane is n equals a b c. Okay, very nice. So we have derived exactly this equation. This is the equation of the plane. This is the equation of the plane that goes through the given point in a space. The point is x0, y0, z0. And not only that, the point is that, okay, so the point goes through a given point, but also the normal vector to this plane is the given one, the one that they gave me. This is the normal vector n. So the plane is unique because if you just specify a point, there's so many planes that goes through a given point. But when you specify a point as well as a normal vector to this plane, then you specify the plane uniquely. And that's exactly the equation of this plane. Okay, let me give you an example of how to find equation of a plane that goes through a given point and has normal vector maybe 1, 2, 3. So for example, find the equation of a plane. The plane is supposed to go through this point 2, 4, -1. The plane is supposed to go through this given point. They gave me this point, and also they gave me a normal vector to this plane, and the normal vector to this plane is 2, 3, 4. So, well, let's see. If I have a normal vector, A, B, C, this is the normal vector, then I put the coordinates simply here, A, B, C. And then I'll have x minus x0, y minus z, y0, z minus z0. x0, y0, z0, that's the given point. Okay, so since we have derived this formula, then this is very simple. The equation of the plane is, okay, so the normal vector n was 2, 3, 4. 2, 3, 4. That was the normal vector to this plane. So we use those components A, B, C, in this example 2, 3, 4, to put them here. This is the first one, 2, this is the next one, 3, and this is the last one. And then we also have this given point, x0, y0, and z0. This point in this example was supposed to be 2, 4, and -1. 2, 4, and -1, -1. So this is going to be x minus 2. This is the first point. And then y minus 4. This is the second coordinate. And lastly, z minus and minus -1, so z plus 1. Okay, so that's the equation of this plane. And then when we simplify this equation, then we get 2x plus 3y plus 4z plus 12. This is the equation of this plane. Remember, equation of a plane in a three-dimensional space. If you are in a three-dimensional space, then every plane has this equation, some constant a, x plus by plus cz plus d equals 0. Every plane has this equation. And notice that this is indeed a plane. The a is 2, 3, b is 3, and so on and so forth. So this is the plane that goes through this given point 2, 4, and -1. If you, okay, so to check that, if you can take x equals 4, so you have 2 times 4, and then y is supposed to be 4. So plus 3 times 4. Okay, and then z is negative 1. Okay, so negative 4, that's supposed to be equal to 1. Okay, so that's a check. And then it, okay. And then you can check that this vector is a normal vector to this given point. Okay, so let me just say a few words about projections now. What will be, well, it's the same section, but what we'll be doing is essentially, what we'll be doing is essentially this. Let's say we have two vectors. One is maybe A. So maybe this is the vector A. From here to here, this is the vector A. Okay, this is the vector A. Let's take another vector B. And you know, the vectors A and B are somewhere in the space, but I can look at the representative vectors. So I can bring them to one point, to the origin. I can bring them to one point. So let's consider another vector B, and maybe I'm looking at the representative of this vector. So they are both attached to the origin of the coordinate system. So this is another vector B. And what do we mean? This is another vector B. What do we mean by a projection? What do we mean by the projection of this vector A onto this vector B? Projection is going to be, well, we'll have scalar and vector projection, but let me say vector projection. So this is the situation. The vector A is given. This is the given vector A. Also, I have this vector B. Those two vectors are given. What do we mean by the projection of A onto B? When we say projection, we always think of as orthogonal projection. There's other projections as well, but we'll be just thinking of, there'll be no ambiguity because we won't be talking about other projections. When we say projection, we mean orthogonal projection. So the orthogonal projection of A onto this vector B is simply we take this point and then we project this point onto this line, but we do so in the orthogonal way, meaning that this angle is exactly pi over 2. And this new vector is exactly this one. This is this new vector. So the direction of this new vector is exactly the same as the vector B. However, this vector might be a little bit shorter or maybe a little bit longer, depending on the context, but the direction will be always the same as the vector B. So, okay, so how we can derive this formula for this vector, for exactly this vector? Well, we'll use inner product. So the vector A was given and the vector B was given. So if those two vectors are given, I can compute the inner product or the dot product of those two. I'm saying inner product for the dot product again, so excuse me, but when I say inner product, I mean the dot product, the same, those two things are the same. So the vector A was given and the vector B was given as well. So I can compute the dot product A times B. A times B is equal to, we know that this is equal to the absolute value of A, or the length of A times the length of the other vector B, and then times the cosine of this angle theta, where theta is this angle between those two vectors A and B. So times cosine theta. Okay, so see, I would like to know what this is. I would like to know what's the length of this. So let's call this for, just for 1 second, maybe, I don't know, x. So if we call this x, then I know that cosine theta, what is cosine theta? Cosine theta is the adjacent divided by the hypotenuse. So let's see, what would be the adjacent in this example? Well, the adjacent would be, let me see, the adjacent would be, if I call this x, the adjacent would be exactly bx. Okay, so this would be the adjacent divided by the hypotenuse, which would be this length, which is the length of A, which is the length of A. Okay, so if I multiply both sides of this equation by the length of A, I get that the length of A times cosine theta is equal to x. So this is exactly A times cosine A times cosine theta. Okay, so we know, at least now we know how long this vector is supposed to be. Let's just find the appropriate direction, because length is not enough to specify a vector. So let's divide both sides of this equation. Let's divide both sides of this equation by the absolute value of b. By the absolute value of b, well, then I have the inner product or the dot product a times b divided by absolute value of b. That's equal to a times cosine theta. Okay, but a times cosine theta is exactly this. Okay, so now what I want to do, let's look at this vector b. This is the vector b, and let's normalize this vector, because I don't know what is the length of this vector. Let's normalize this vector in a sense that let's shrink this vector to unit 1, so that the unit of this vector would be 1. So this is the vector b. I can compute the absolute value of this vector b. And I can look at this number 1 over the absolute value of b times b. So what is this? This is the normalization. This is the normalization of this vector b. This is the normalization of this vector b. And what it means is very simple. See, if the vector b was given, maybe the length of this vector is 17. Then this new vector, which is, so that was the vector b, and this new vector 1 divided by the length of b times the vector b itself, this vector is exactly this vector from this point up to that one, but it has length 1. Because compute the length of this vector. Well, the length of this vector is going to be the length of 1, which is 1 over b times the length of b, which is 1. See, so this length of this vector is equal to 1. Okay, so now we have this vector, the given vector. So the given vector is a times b, the inner product of those two divided by b, times the normalization of this vector b. Okay, that's exactly the projection, the orthogonal projection, we should say, but we'll be just discussing only orthogonal projection. So that's an orthogonal projection of A onto this vector B. So do I have some example of that? Yes. We have some example, and it's okay. Let me just mention the scalar projection. The scalar projection is just this number itself. So just this number itself is the scalar projection, and the vector projection will be this scalar times this vector. Okay, so scalar projection is the result is a number. So this is a number. And the vector projection, the result is a vector. So this is a vector. So again, if this is the vector A, the green one, the blue one is the vector B. That's the projection of this vector B onto this vector A, This is also projection, and this is the scalar projection. So let me give you an example that will be clear. And let's say that we want to find the scalar projection as well as the vector projection of this vector onto A. Well, okay, so we can compute the scalar projection and vector projection following those formulas. Okay, so let's see. That's all what I want to say about this section.